Hello everyone, my name is Tiago Davi Curi Busarello. I am a professor at the Federal University of Santa Catarina, Brazil. In this video I will show you the model I developed in Typhoon software. This is a part of the requirements for the 10 HILs for 10 Typhoon Years Program. So here I have some member of the teams, students from graduation and undergraduation. So the model I developed is a multifunctional grid-connected inverter, which is a grid-connected inverter able to operate in 7 different modes of operation. So first I compute the references from the 7 modes, and I can choose among these modes in order to make this grid-connected inverter perform multifunctionalities. The point here that I am using the conservative power theory to compute some references, and I have here only one current controller able to operate in the 7 modes. I mean, this current controller is able to make the output current of the inverter follow its signal reference. The modes of operation from this multifunctional converter are active power injection, full active filter, reactive power compensation, harmonic compensation. We can combine some of these functionalities and produce here a mode of operation called active power injection plus reactive power compensation. So this is simultaneously performing 2 different tasks. Active power consumption plus reactive power compensation. Notice also that this grid connect inverter is able to inject power and consume power, and there is also a mode of operation called standby, which means that the converter does not do anything. And some features of this model is that there is no need for physical changes in the power structure for the 7 modes, and just one current controller. Going here through the model in the schematic, I have here a description. I will give you a short description of that. So I have here a grid, which is single phase, 50 Hz. And also I have here line impedance. Here is the multifunctional grid connected inverter. I'm using here a half bridge inverter for simplicity. I have here the output filter, and I have here also a load current. I have 3 measurements of this power system, which are the grid voltage, the output current of the inverter, the load current. After measuring these three variables, I have here the control strategy. So by measuring the voltage and the load current, I can compute here the 8 references for the multifunctional inverter. So I compute 8 different references. Notice that some references are a combination of them, and also have here the reference 8, which is a null constant, which makes the converter to be in a standby mode. Some features here is that I used the PLL of the simulator, which is really attractive. I have here a SCADA input just to make some transient analysis. I'm using here also a C code that I typed in this block. This C block here, C code, is for measuring the average value of its input. Have here again. So the point is, I measure two variables, and then I compute 8 different references, and then I take these references to this multi-port signal switch, so I can choose in what mode of operation the converter will operate by selecting properly the number later in SCADA of this variable here. So just one reference passes through this signal, multi-port signal, and later I compare with the inverter output current, and then I pass it through the current controller. So this is the values of the Z-domain transfer function, which operates as a current controller. And a point here that I'm using is that the switching frequency is 25 kilohertz. So, and the execution rate is 1 microseconds. However, all my control strategy is running at 25 kilohertz. So I'm using a rate transition with this execution rate right after each measurement. The grid voltage, the load current, and also the inverter output current. So all my control strategy is running at 25K. And later, after computing the output signal of the controller, I'm convert back to the execution rate of 1 microseconds. So notice that independent of the reference I'm choosing, I have just one current controller. After compiling that, I created a model here, a panel in the SCADA. So I have here the mode of operation, and can choose between the modes of operation in this setup here. I have here indicators in what mode of operation the converter is working, and some currents just to notice how they change according to the mode of operation. So I have here the values for the voltages, frequency, and I have here also that SCADA input for transient analysis. If I run this simulation, it begins with active power injection. I can see here some signals. They are the reference for mode 1, for any mode I mean, and the current, output current following the reference. I have here the grid voltage and the load current. The load is distorted, and also the grid current, because it is interesting to see how the grid current results after each operation mode. I have here the error signal from the controller. This is negligible, so just to make some triggering later. I can choose between the modes, among the modes, and I can see here how the current goes for each one, and also an indicator for these modes. So I have here standby. This current is also negligible, and I'm sure I can make some triggers here. I will use the error signal, for instance 0.2, just to check how it changes from, for instance, standby to active power injection. So I can see here the current is actually null before I changed that, and then I can see how the controller makes the output current to follow its reference. So I can also show you the bidirectional capability of this converter. So I'm injecting active power, but if I change this value to -2, I can see how it changes. Oops, sorry, here. Okay. So if I change here to -2, for instance, I don't know what is happening. Let's see again. So forget that. Let me show you another thing. Another thing is that when this kind of conservative power theory I used for using these modes of operation, like full active power, I mean that even if the grid is distorted, I can make the current to follow its reference. So if I include here an harmonic, the third, with such a value, I can see clearly the green line here distorted, but I can see here that the grid current is also distorted, and this is called load resistive synthesis, that makes the grid connect inverter makes the grid to see a resistive load independent of the mode of operation. So go back here to active power injection. I can inject active power even in the presence of harmonics. So this is the model. Hope we understand. If you have some doubts, you can contact me through email. I hope we succeed in this program. Thank you.